So anyway, let's get going. So kind of how I got into this. I started working with a guy named Peter Rumsey. I don't know, some of you must know him. Back in like 2000, and we did like we didn't even realize it at the time, a net zero electric school building with like peel and stick PV on a standing seam metal roof.
Super forward thinking.
Yeah. And then, in 2002, we did I did my first LEED Platinum building up at Lake Tahoe. We did an office that was with EHDD, and we bought this office, and Scott Shell, the architect's like, oh, maybe if we make it really energy efficient and put PV on the roof, we could generate enough electricity to offset the energy use. We could call it something like net zero energy or something like that. So that's how that's how it happened. Actually, the longer story is, so I was like, I think I want LEED Platinum, Scott. Let me think about that. So I went home over the weekend, and my ex-wife's like, when you design LEED Platinum, what do you do? I was like, well, most of it's other stuff. She's like, so what part of it do you do? I was like, well, the energy efficiency. So she's like, so if you do net zero energy, isn't that focusing on what you're good at? I'm like, oh yeah, that's a good idea. So that's how it ended up being net zero energy. It wasn't me. And then we did a bunch of net zero, and then in 12, we got this project, and it was net zero, but it was a for-profit building, which was pretty interesting. So, suddenly we're doing it on a budget, you're doing it at kind of market rates. 2016, we did an interesting microgrid project in Hawaii. And the reason we did a microgrid wasn't because we're trying to do cool stuff. It was because it was too expensive to upgrade the utility service to put air conditioning on a bunch of classroom buildings. And it was cheaper to put PV and a battery on the classroom. They've done like a couple of thousand classrooms now using that concept. And then more recently, we started doing all electric kitchens. And wax, right? Microsoft. And actually, this is a study that I worked on that we kind of studied it for Google, and they signed off on it. And during construction, they actually made the decision to change this building from a gas kitchen to an all-electric kitchen, and now they're all electric. We did the Microsoft campus in Silicon Valley. That went gas, but we convinced them, and then after that, their next big project up in Redmond is all electric also. So 2 major tech companies are all electric now. And then last year, we did this really interesting study looking at an electric bus fleet. And they're actually starting to go, A, they're going from gas to electric or diesel to electric, but B, they are putting in V to G chargers and starting to play around with SMUD and try to support the grid with that. So that's really interesting. And we actually have a grant application out to do a project that'll be able to use those buses to act as part of a microgrid in the future. And the thing I'm working on right now, and some of my presentation talks about this a little bit, is electrification of an existing residence block of apartments that has 100 amp panels. And then somewhere along the line, climate change became a design thing, right? That suddenly we're not just designing buildings, we're designing for climate change issues. So a couple of key facts. One is I've been thinking about carbon on the grid, right? So, we're talking about decarbonization and electrification, but if you have a lot of carbon on the grid, that's an issue. So US is actually pretty good. Not as good as Iceland, which has got no carbon on their grid, but much better than South Africa, which is like the worst of the data that I looked at. And California is really good, but actually has a lot of natural gas for generation, right? So there is some carbon on our grid. Great thing is the cost of PV has been going down, and the cost of batteries has been going down. So now we're talking about both putting PV and batteries on projects in California, right? So I got this interesting project. Sean's actually helping me with it. It's an off-grid project. And I thought, this will be really technically fun, but kind of a waste of time because nothing's off-grid for the most part. But actually, it made me think about California's grid because some of the issues with an off-grid house are kind of the same issues with the state of California, I realized. So I've presented this slide a bunch of times. This is like, this is the grid, and this is like, for each month, this is kind of the average. And you're starting to see like different times of the day. These are the hours of the day. This is like each month of the year. For different times of the day, there's like times of the day where the grid's cleaner and dirtier. So you could charge a battery when the grid's clean, discharge it when the grid's dirty. That's not the issue, though. I mean, that helps, but that's not the issue. So, this is what I presented at other conferences. So the issue is that this is my office. If we're going to this is my old office, that Net Zero Energy office, a year's worth of information. If we're going to an all-electric future, right? All that information that you're looking at back here, this is not an all-electric future. This is like today's grid with today's energy use, which is mostly gas in the winter, which looks really good. But that's not how it's going to be in the future. So I think one of the things is trying to think about not just like what things are like now, it's like what things are going to be like when all these changes happen. So this is my office. I don't have tons of data on all electric buildings, but here's two data points. This is roughly the same energy use summer and winter, right? You could say, right, this green line. This is my house. Way more energy use in the winter. This is in Cupertino where it actually doesn't get that cold. And then this is my PV production. So classic duck curve, right? It's like over-generating in the summer, so that doesn't actually work very well, right? Because it's like we don't have a good way. Sean and I were just talking. There's not that many good ways to store energy from the summer and use it in the winter, right? So here's that same curve again. I tried to fake out what would it look like if all of California were electrified, and I'm guessing it would look something like this, right? So suddenly you got a lot of energy use kind of at night in the winter, and that green kind of went away except in the spring. So the thing I was looking at related to what Sean and I are doing is like, my PV is generating at the wrong time. I want PV that generates a lot at night. Oh, I'm sorry, a lot in winter, not at night. So we started looking at, for this project, changing the angle of the PV array. This is, what was that up to, 60 degrees, and this is like flat. Taking them and tilting them up toward the south, right? So, and I found some website that claimed to give you the best angles for different like for winter and summer. So I don't know if it's bona fide or not, but I use those numbers. So it says best annual is 31, this is for Cupertino. Best annual is 31 degrees, best summer is 13 degrees, 13.7, and best winter is 51.8. So if you're trying to optimize for winter, you tilt it way up, which makes sense. If you try to optimize for summer, you flatten it down, which makes sense. And annual is somewhere in between, which makes sense, right? So I looked at if that for my office building, what's the energy use, which is the yellow bars. And then I looked at kind of optimized summer and optimized winter. And you can see that if you optimize a PV for winter, at least you're getting a lot closer on the generating the energy when you need the energy, right? If you optimize for summer, you have way too much energy in the summer and way not enough in the winter. So the other thing that got me thinking is looking at the grid and utility scale PV and what angles are those installed at, right? Because that's where you really want to try to, you want the utility to be optimizing for the grid overall, not for summer or for profit, right? So, good point. So this is if you optimize for summer. So a lot of these big arrays in the valley are optimized for summer, which is when the rates are highest, right? This is optimized for annual.
That's a lot of it.
Which is so that covers almost everything, right? And so, but if you optimize for winter, where would you be? That's optimized for winter. So nothing's optimized for winter, right? And a lot of it, I guess, is money. So I guess the question in my mind is, as we electrify everything, is that going to become a huge problem, or can they just change the tilt angle like 10 years from now for the existing arrays? And then the other thing is, Sean's doing the wind design for me. So I was like, maybe wind turbines can take up the slack, which on our project, it looks like it can, but on this project, but overall, this is Northern California, Southern California. It peaks in early summer, late spring, surprisingly. I thought it would be really good in January, February, but it's not. So you can't count on wind to solve the problem, best I can tell. And this, the last slide of the series is, this is PV generation. See those little gray things there, right there? That's curtailment. So you can see the way the arrays are laid out right now, they're already curtailing in the winter a little bit. But that's because they haven't, we haven't electrified yet. So there's not huge electrical demand in the winter yet. But you can see in the summer, even though the production's higher, there's no curtailment yet. So there's this kind of, the thing that we really need to be thinking about is as that electrification happens, then this whole curve's going to change, and when their curtailing is going to change. Okay. Next thing I've been looking at, I'm doing a project, I'm looking at existing residences and electrifying them. And all these residences have 100 amp panels. It's a apartment block in Redwood Shores. So the first thing that really shocked me was peak demand, looking at 50-minute interval for a year, was 19.5 amps.
The whole building or per apartment?
Per apartment, per apartment. 19.5 amps. I was just like, are you joking? But that's what it is. And so when you do the NEC calc on it, you've got 75% of the panel as spare capacity. So then when I looked at kind of what can I put on, we want to put on a heat pump water heater, a heat pump dryer, and an induction range. Those 4 things. And I was like, geez, that's not going to fit, but it does. Actually, no. It misses for this one, the 19.5. it misses by half an amp. But essentially, you can get there. You just have to pick one device that's a little bit more efficient. Actually, the calc I did that didn't quite get there didn't have a heat pump dryer. It had an electric resistance dryer. So if you pick your equipment efficiently, you can get there. That's good news. Then the other thing is, even if you can't get there, there's starting to be equipment out there. So SPAN makes this really cool panel. It's kind of expensive, but it's very smart in that it can, once you start reaching a limit, it can start flipping breakers off, and you got prioritized breakers and do all kinds of really interesting things. But this company here, I think it's called Simple Switch. They make a switch that it's just a dumb switch that you turn two things on and one of them's prioritized and it won't let you turn the other one off, right? Which a couple companies make, but they make something that's even more interesting, that it's got CTs attached to it, so it won't turn anything off unless your panel's maxing out. And then it'll turn stuff off. So I'm thinking if you use that and connect all this equipment and just put the largest load on that CT, it'll never turn off, right? Because the chances that you're using everything and load the panel all the way up if you only had 19.5 amps when you started is practically zero. So I think this switch might be a really good, fairly inexpensive answer for this project. And then SPAN makes their panel can also take a battery. So you could potentially do stuff where even if you were to go above 100 amps, that the battery can kick in additional power, and you're getting power from the utility plus power from the battery and run even larger loads.
Can you do that now?
I think so, right? It's just the panel's got to be able to have larger bus bars, right? Like if you have 100 amp service and 200 amp panel. So conceptually, you could do something like this, right? Have a building, put in this system, and then start putting all these loads in. And then the other advantage to that, of course, is if the grid goes out, boom, you could still run your house. And as Sean was saying, nowadays you're going to start being able to use the car as your battery. Okay, so then the last thing I wanted to talk about is we're starting to look at EVs now, right? And your team gave me a lot of good information on this, and a little bit of it's repeat, but I wanted to touch on some of this. So key thing is that transportation is a big issue, and as we electrify, it's going to have major, major impacts on the grid, right? And so China is now the leader in EVs and potentially is set to dominate. So batteries and EVs, one of the things that I see happening is, I don't know if any of you were paying attention like about 15 years ago when PV started becoming a thing. There's a company, Solyndra, that had this really cool technology. It got all this publicity. It was like half the price of regular PV. And I was like, oh, that sounds brilliant, right? That's good. That company's going to dominate. And then a year later, they went bankrupt.
Yeah. So
what happened? Why did that happen? Other than the technology was a little bit shaky.
You want to know? I don't know.
So the cost of China started building more and more and more PV manufacturing, and the cost just fell through the floor, right? That graph that I showed of PV, that was China building lots of capacity. It got so bad there, Chinese companies were putting each other out of business. And so Solyndra didn't plan on the cost of PV going down to a fraction You know, they were good if it went down like 30%. They weren't good if it went down like 70% or 80%. The cost of PV dropped so much it put other manufacturers like Cylinder out of business. So, you know, I could see that happening in China with batteries and EVs now, right? Because it's like BYD and there's a bunch of Chinese companies that are making low-cost EVs that are going to, not to the US, but to other countries. So, you know, this is the US, right? Huge amount of energy going into transportation. As that electrifies, then we need to be able to supply electric power for that, right? And you know, EV sales are going up pretty rapidly, with California leading. So I think some of the key trends we need to be thinking at are, right, in Mountain View and in the Bay Area, they now require 100% of parking garages, stalls to be EV ready, 100%, right? So they're planning on, it's like a world of all EVs. Right, and those loads can easily exceed the buildings that they're attached to. I was working with Google, and like just their, like one of their small buildings on the side, they started putting EV charging in, and the peak demand went from 4 in the afternoon till 9 in the morning. And there's not that many chargers in the parking lot, right? So it's like if they had chargers at every spot in the parking lot, it would just skyrocket, right? And you know, right now the chargers are kind of dumb chargers that aren't controlled. So controlling chargers is a big thing. You know, employees expect free charging in a lot of these tech companies. So there's this whole discussion of what happens and how does that happen. But the other thing is, with PV, that's when you want to charge anyway, right? That's when the peak generation is. So ideally, you're charging, the best time to be charging EVs is going to be in the middle of the day anyway. And the cool thing is there's starting to be some really interesting software out there for managing how that happens, right? So, you know, you want to be charging middle of the day, right? So there's this, so this is kind of the traditional charging system, right? You just plug in and it charges and you get what you get. But there's, so, you know, when you do this, it's easy to overload your service. So one of the things is that like companies like ChargePoint were doing is just putting in chargers that you're sharing 4 chargers on one circuit. So if you have 4 cars plugged in, you get a quarter of the energy, which you know, that's fine. It limits your maximum demand, but then sometimes your car doesn't get charged up, which isn't ideal. There's another company out there. Actually, there's starting to be a couple of companies that are doing this. One of them is called PowerFlex, that they can actually manage what gets charged when. So you got to tell them when you need the car back, and they look at how much charge the car needs, and it starts juggling. If you don't need your car until 5 in the evening when you're going home, it may wait until 3 in the afternoon to start charging your car to try to balance that out, right? So it's kind of smart charging, and it flattens that demand curve and shifts stuff till later in the day, which will save you on maximum demand. And actually, the guy's a Caltech grad, I talked to him and I was like, you know what you really need to do is take a building and look at the maximum demand on the building plus what the cars need, and flatten that whole curve, not just what the cars need. And he's like already working on it. So there's some really interesting, smart things that potentially that kind of software can do. And then the last thing, you guys kind of talked about this, is Ford's coming out with something that's made to be a microgrid. And so you could actually connect to the house, as you were saying, but and put PV on it and run the PV with the Ford. So that's a really interesting new thing, and presumably everybody's going to be doing that in a couple years, I assume. And like I said, we're doing this project in Sacramento that's using buses, and we're looking at doing similar types of things. But as you can imagine, if you have 80 buses, that's a lot of power that you can start playing around with for the utility or for supporting schools if there's a power outage, that kind of thing. So, schools can kind of like, there's this, school buses are really good because there's this gap in the middle between when they pick up kids and when they deliver them back home again, that they could just be using that for either charging or supporting the grid and things like that. So, I guess the last thing I want to throw at you is between electrification, which is mechanical engineering, PV, EVs, and battery storage, there's a lot of interesting changes happening. Those things are going to totally change how the grid works. So this is the team to go out there and come up with new ideas on how to use this stuff. So thanks.
So that 19.5 maximum demand for an apartment, was that an all-electric apartment or a okay, mixed fuel?
Gas heating, gas stove, gas water heater.
One thing that concerns me a lot is that heat pump water heaters, space heating heat pumps, and heat pump clothes dryers are by and large almost all hybrid, in which you, in addition to having the heat pump, you have electric resistance backup. So I think an important thing to do is to start moving towards things that don't have electric resistance backup, like 120 volt heat pump water heaters, and also for space heating and clothes drying. Because otherwise we're going to get these large demands. Even though we have these very efficient heat pumps, if we drive demand way up with these hybrids, and so I think that we should be moving away from these hybrid devices if we can.
I hear you, and at the panel, like at the individual unit level, I agree, but I think presumably that's only for very short amounts of time, right? And I get that it's less efficient, but when you look at it at the building scale, might be less.
Because it's statistically distributed.
And it's still resistant, so it's still less efficient. But I'm wondering how much time it's actually.
You have to size your panels in order to handle that.
Yes, but I mean, I was surprised when we looked at it. When I did my first calc, I was using like 240 volts, 20-something amps for an electric resistance dryer, and that's the calculation that it just came in a tiny bit over what the panel could handle. With an electric resistance dryer, as soon as I changed it to a heat pump dryer, it worked. So, it's not ideal, but, and I agree, like the thing that worked best was a 120 volt heat pump water heater, and then it just, the loads went way, way, way down.
Does the winter solar issue start to make single-axis tracking make sense again, or is that just
single-axis tracking typically is laid out north-south, and it's going morning. It's like helping in the morning and the afternoon. You know what I mean? This is like tilting it to the south, not to the east or the west.
Right. So that's what I'm talking about. So seasonally changing that angle rather than.
Yeah.
Does that make any sense, or is it still just too expensive? Solar's too cheap. 10 years from now, or 20 years from now.
It might. I don't. Actually, probably not, because in the summer, I don't think you're gonna. You don't need the power.
Yeah.
I think. In the future, you're going to have, you're going to have curtailing in the summer, I think. Right? And one of the interesting things we never talk about is, right, with natural gas, they build peaker plants, right? They put in a plant, they keep it turned off most of the time. And it's just only turned on if you have a really hot day in the summer to give you a little bit of extra electricity, right? When's the last time you heard somebody talk about a peaker PV system, right? That you only turn on when you need power.
Yeah, but that is one of the emerging concepts in solar is
Yeah.
Don't get all in a hissy fit about curtailment because
That's what they
the
do with
fleet-wide
gas.
storage of natural gas is actually less than 20% capacity
Yeah.
utilization.
Yeah, I agree.
So, I guess two questions. One, I assume that solar now is all designed to maximize summer output. And you're saying
I think it's designed actually, I don't know for sure, but I think it's designed to maximize for
for money, you're saying
payback.
it's summer output.
Yeah.
So, are you thinking there'd be a point where it would make sense to start transferring to maximizing for winter output? And then, I guess secondly, is how does this interact with like the cost of the storage of like, it doesn't matter when you generate the solar, you just put storage and deal with it.
You're going to see a presentation on our off-grid apartment complex, almost off-grid apartment complex, and Dylan on our team, he tried doing the shading analysis of what if we point the panels up, more so it works in the wintertime, and they shaded each other. I mean,
you got to
we
spread
just
them further apart. Right?
Yeah, so it didn't work out.
It's not easy.
We couldn't put them up like that because all the panels behind them didn't get sunshine. So it made much more sense to keep them flat, even though we lost the efficiency in the winter because we still got sunshine on all of the panels.
It's not simple.
And then you think storage is balancing off the solar?
Are you going to talk about that in your presentation? Or no?
Oh, which part?
Storage, seasonal storage.
Oh, not really. I wasn't going to.
So I'm not a mechanical engineer, but Sean's done some seasonal storage projects. That's not easy either. The other Sean Orm.
And even daily storage, you just,
Daily storage,
offsets the fact you get less
Yeah.
in the winter, you just buy more storage to offset.
yeah, daily storage is makes sense and is easy with batteries and relatively easy. Seasonal storage is the difficult thing. Okay.